Have you ever wondered, is light a particle or a wave? Welcome to the fascinating world of quantum physics, where light, strangely enough, behaves both as a particle and a wave. Known as the dual nature of light, this concept is one of the cornerstones of quantum theory. It's a world where particles can be in two places at once, and waves can act like particles. This dual nature of light has been a subject of debate for centuries, and it's not as straightforward as it might seem. Let's delve into a phenomenon known as the photoelectric effect. This intriguing occurrence is when light, or more specifically photons of light, strike the surface of a material and eject electrons. Picture it like a game of billiards, where the incoming light particles are the cue ball, and the electrons are the balls scattered on the table. The wave theory, prevalent in the 19th century, postulated light as a wave, much like ripples on a water surface. However, this theory stumbled when it came to explaining the photoelectric effect. According to the wave theory, a light wave's intensity should determine the energy of the ejected electrons, meaning brighter light should eject more energetic electrons, but that's not what happens. Instead, the energy of the ejected electrons depends on the light's color or frequency, not its brightness. This baffling discrepancy led scientists to question the wave theory. The wave theory fell short in explaining the photoelectric effect, leading scientists to think differently about the nature of light. Enter Albert Einstein with his groundbreaking interpretation of light. Einstein, a name synonymous with genius, proposed a new way of understanding light, radically different from the wave theory. He suggested that light is composed of discrete packets of energy, which he called photons. This theory was revolutionary because it went against the prevailing wave theory of light, which struggled to explain certain phenomena like the photoelectric effect. The photoelectric effect is the emission of electrons when light shines upon a material. The wave theory predicted that the energy of these electrons should increase with the intensity of light, but that didn't hold up in experimental observations. Einstein, by proposing that light was made of individual photons, provided an explanation. He suggested that it's not the intensity, but the frequency of light that determines the energy of the photoelectron. Each photon has a specific amount of energy determined by its frequency, and when a photon hits an electron, it can transfer its energy, causing the electron to be emitted. This idea was encapsulated in Einstein's famous equation, E equals h times v, where E is the energy of the photon, h is Planck's constant, and v is the frequency of light. Einstein's quantum theory of light not only explained the photoelectric effect, but also set the stage for the development of quantum mechanics. It was a bold leap forward, forever changing our understanding of the universe and the very nature of light itself. But what about the red border of the photoelectric effect, you might wonder? Well, the red border is a fascinating concept that further proves the particle nature of light. You see, the photoelectric effect is all about electrons being ejected from a metal surface when light shines on it. But here's the catch. This only happens if the light has a frequency above a certain threshold. This threshold frequency is called the red border. It's the point at which the energy of the incoming light is just enough to overcome the work function of the metal, the minimum amount of energy needed to eject an electron. If the light frequency is below this threshold, no electrons are ejected, regardless of the light's intensity. This behavior contradicts the wave theory of light, which would predict that any light intensity would eventually eject electrons given enough time. But in reality, it's the light's frequency, not its intensity, that matters, reinforcing Einstein's quantum theory. The red border of the photoelectric effect provides compelling evidence for the particle nature of light. This quantum theory of light isn't just an abstract concept, it has real-world applications. Let's delve into a few. Solar cells, for instance, heavily rely on the photoelectric effect. When photons of sunlight strike the solar cell, they knock loose electrons, creating an electric current that can power our homes. Next, we have digital cameras. Ever wondered how a fleeting moment is frozen forever in a photograph? It's all thanks to the quantum theory of light. When light hits the sensor in the camera, it causes electrons to be released, which are then converted into an electric signal and processed into an image. There are countless other applications of the quantum theory of light, from medical imaging to data transmission in fiber optic cables. All these technologies that we take for granted would not be possible without our understanding of light's quantum nature. From powering our homes to capturing precious moments, the quantum nature of light plays a crucial role in our everyday lives. So let's recap what we've learned today. We delved into the dual nature of light, exploring its wave-particle duality. We analyzed the photoelectric effect, which challenged traditional wave theory. We ventured into Einstein's quantum theory of light, a revolutionary concept that reshaped our understanding. We examined the red border of the photoelectric effect, a crucial output operation. Finally, we highlighted the practical applications of the quantum theory of light. The quantum nature of light, a concept that once baffled scientists, now forms the backbone of many technologies we take for granted. It's a perfect example of how understanding the mysteries of the universe can lead to practical applications that benefit us all.